Assalamu alaikum dear students, welcome to the lecture of the classical mechanics. In this lecture we will discuss the solution for the problem number 7.14, which says that a simple pendulum of length b, same as problem number 13, and bob with mass m is attached to a massless supports moving vertically upward with constant acceleration a. Determine the equation of motions and the period of small oscillation. In this case, our that sample pendulum uh, is accelerating in upward direction with acceleration a. Over this acceleration with a, so now this will contribute in the y direction in the equation of motion, and it will change the generalized coordinate for along y direction. So in this case we have again that sample pendulum, and if I show you that diagram, so it is just like this. This is sample pendulum of length v, and it is making some inclination theta because definitely it will have to oscillate, and it is moving with acceleration a upward. So our x direction motion will be equal to b sine theta because in the front of theta it will be sine theta, and y will be equal to 1 by 2 at square minus b cos of theta, because b cos theta will be in this direction, and 1 by 2 at square because its acceleration in the forward direction, so it will be positive in the upward direction, 1 by 2 at square minus b cos of theta. So we can take it derivative for x and y. It will be x dot is equal to this and y dot. Then we can find its kinetic energy by using formula m over 2 x dot k square plus y dot k square, and putting that the values of x dot and y dot. This will yield m over 2 b square theta dot square plus a square t square plus 2ab t theta dot sine theta. Then we can find the potential energy, which is equal to u is equal to mg y, and we know the y is equal to this mg at square over 2 minus b cos of theta, so it will lead to this equation. Then Lagrangian will be equal to t minus u. When we substitute the value of kinetic energy and potential energy in this expression, so it will give us Lagrangian is equal to this whole term. Then if we put this Lagrangian into Lagrange equation for theta, it will give us d over dt mb square plus this whole term and this whole term. So it will give us equation of motion theta double dot plus a plus g sine theta over b. For small oscillation, so sine theta will be equal to theta, so we can put sine theta equal to c theta. That will give theta double dot plus a plus g into theta over b is equal to this. And if we compare this with equation, standard equation, theta double dot plus omega square theta is equal to 0. So if we comparing this two equation, it will give omega square is equal to a plus g over b, and we can find there from that omega time period is equal to 2 pi over omega. Here we can find the time period 2 pi, and omega is equal to a plus g over b whole under root, so it will give us expression for time period. And this was a very simple question in which just we have to take the equation of motion for x and similarly equation of motion for y. Then this is the whole derivation we have done for x dot, for y dot, and for kinetic energy, which is equal to m over 2x dot k square. We have related here the expression for x dot, and similarly for y dot contain two terms, so definitely its square will be equal to a square plus b square plus 2ab, and we can simplify further by taking here b square and theta dot square common, and in these two terms, so when we take this b square theta dot square common, so we will left with sine square plus cos theta, which is equal to 1, and plus other term. So we can simplify, that b sine square plus cos square theta is equal to 1, and other term is written as it. And for potential energy u is equal to mgy, we have already expression for y. We have to just substitute in this, and we'll use y. Then Lagrangian, this sine square, this mb square over 2 and this mb square over 2 is common, and this theta dots along with theta dot square. So we will left sine square plus cos square plus this term and this. This is Lagrangian. We will put just this into Lagrange equation, which is shown as below. Partial L over partial theta dot, which is equal to this, and partial L over partial theta, which is equal to this. When we put into Lagrange equation for theta, so d over dt partial theta dot minus d over dt partial so d over dt partial or partial theta dot Lagrangian is equal to this whole term, so it will give this. And then in Lagrange equation, you know that d over dt partial L over partial theta dot minus partial L over partial theta, which is equal to 0. We will need this term also, because we have calculated this term, which d over dt partial over partial theta dot, which is equal to this. Similarly, we need to calculate this if we find more equation of motion of partial L over partial theta is equal to this. We have already calculated partial L over partial theta. As you are looking that this is partial L over partial theta, we will put this equation, this expression and this into this Lagrange equation, and it will give our required expression for the equation of motion, which is this. This is the whole derivation. We have simplified it, d over dt partial is equal to this, and we have obtained this equation theta dot plus this. Then you can do this by evaluating in this sine theta with the help of Taylor series. So sine theta will be equal to theta minus theta cube plus 3. For small oscillation, we can neglect the higher order term and take only first term, so it will sine theta will be equal to theta, and putting this in this expression, so we will get theta double dot plus a plus g over b into theta is equal to this, or just theta double dot plus omega square theta is equal to 0. And you know that if we compare these two equations, so this will be omega square, so omega square will be equal to a plus g over b, and here we can evaluate this for omega, which will be equal to a plus g over b and whole under root. So you know that time period is equal to 2 pi over omega. We will put the value for this omega, which is equal to a plus g over b into this, and this will yield expression for time period.